All right, for question 12, right, it gives us two of the bases, guanine and cytosine, right? So that GC pair in DNA, and it's just asking about the hydrogen bonding arrangement. And so what's a little bit frustrating is they've flipped cytosine away from its normal direction. So normally cytosine wants to be over here like this. So there's our carbon-carbon double bond right there. So all I've done is just kind of flip the molecule that way. We're going to have nitrogen there with its lone pair, and then we've got our carbonyl here with its lone pair, nitrogen. All right, carbon is there. So normally cytosine will be facing that way, and that's going to help us see these hydrogen bonds much more clearly, because we've got hydrogen bonds basically between that hydrogen and that lone pair of electrons, this hydrogen and that lone pair of electrons. And now that I do that, I think I'm just going to make these another color so they show up a little bit better. So that hydrogen, that lone pair, that hydrogen, this lone pair, that lone pair, and this hydrogen and nitrogen. So GC make 3 hydrogen bonds because they have that pattern of hydrogen bond. We have a hydrogen bond donor and acceptor. And then here we have an acceptor and a donor. Here we have a donor and an acceptor. So that just so happens that they match up those lone pair of electrons on an oxygen or a nitrogen match up with a hydrogen connected to a nitrogen. That's what we need for hydrogen bonding interactions. So we get a hydrogen bond between oxygen 3, hydrogen, right? That's hydrogen 3. That's nitrogen 4 with hydrogen 4, and then that's oxygen 5 with hydrogen 5 for that hydrogen bonding pattern in question 12. Again, it's a little bit hard to see because they drew the molecule. They really should have taken the molecule and flipped it the other way for you to make it a little bit easier to see how things are pairing up or are supposed to pair up in that GC pair. All right, so of those choices, yeah, it should be right choice E, because it was 3 paired with 3, 4 paired with 4, and 5 paired with 5 in that structure. Question 16. Yeah, question 16. This came up in office hours. It's kind of a tricky question, I guess, in how it's worded. Which of the following molecules is hydrogen bonding likely to be the most significant component of total intermolecular forces? And just be careful. I think this came up in office hours. There are 2 other versions of this question, so your question might not exactly be this question. So it's asking, right, which one of these is hydrogen bonding the most significant component of their intermolecular forces? So right off the bat, I can cancel out methane, I can cancel out carbon dioxide because those 2 don't have hydrogen bonding at all. I do have hydrogen bonding here, here, and here. And the key to the question is most significant component. So the answer to that is going to be D, methanol, because if we look at the molecule, it's a really small molecule, right? Like half of this molecule is the hydroxyl group. Because of that, because half the molecule is the hydroxyl group, right? That's where most of the intermolecular forces are going to come from, is that hydroxyl group. The other 2 molecules, they've got larger chains, right? They've got 5 carbons, 6 carbons, 13 hydrogens, right? More carbon, more hydrogen. They're going to have other intermolecular forces. They're going to have more London dispersion forces. So, we can't really put a number on it, but if you just want to look at the molecule and like split the molecule in half, right? We could say it's like 50% here Whereas this nitrogen, is 1 out of 7, or this oxygen is 1 out of, 6 places for intermolecular forces. So here, we're like all the way down to 18% maybe if we were splitting it that way. So yeah, it should be the methanol, right? Hydrogen bonding is the predominant intermolecular force there because the rest of the molecule is so small. We're going to have a limited number of London dispersion forces. Yeah, question 23 is already on the list, Mike. I mean, yeah, 17 is on the list too. I kind of wish, at the start we got these questions, right? I polled everyone, what do we want to do? So jumping back to 13, right? We're going to assign boiling points based on, how do we assign boiling points to substances like question 13? Does it have to do with number of atoms and molar mass together, right? So this case, let's say they're all about the same size, right? For question 13, yeah, methanol is a little bit bigger than methane. The key to assigning boiling points in this example, where they're all about the same size, it's going to come down to London dispersion forces. It's going to come down to intermolecular forces, right? Methane is nonpolar. London dispersion forces. Hydrogen sulfide is polar, so it has London dispersion forces and dipole-dipole. Methanol is very polar. It's got hydrogen bonding, right? So it's going to have London dispersion forces, dipole-dipole, and hydrogen bonding. So fewest, weakest intermolecular forces, the lower the boiling point. So methane is going to have the lowest boiling point, right? Minus 162. Hydrogen sulfide is going to have a little bit higher boiling point because it's got a little bit more polarity there and a little bit more molar mass than methane. And then the highest boiling point is going to go with the highest, the strongest intermolecular forces. So hydrogen bonding, right? So yeah, it's going to come down to two things, Riva. It's either going to come down to stronger the intermolecular force, stronger the higher the boiling point. Or if the molecules given are of drastically different molecular weight, then it's going to come down to that molecular weight, right? Larger molecules are going to have more intermolecular forces and a higher boiling point. Yeah. Who else asked a question? 14, right? So 14 is going to be similar to 13 here. Wonderful. Doesn't show up on the same page. So we had, I think methane was up here. Right, so methane is just choice C. It's London dispersion forces. So yes, you can have multiple intermolecular forces, right, available like I listed in the previous thing. So water is polar. Water is already matched up with its answer because all molecules have London dispersion forces. Water will have London dispersion forces. It is polar, so it has dipole-dipole, and it has oxygen connected to hydrogen. It also has hydrogen bonding. Right, the next one, we've got carbon-fluorine bonds, carbon-chlorine bonds. That makes it polar. So we're going to have dipole-dipole forces. And because everything has London dispersion forces, we'll have London dispersion forces as well. And yes, there are two choices you don't need to use for question 14. All right, so here's another example of that same type of question, right? For question 17, we're asked to rank the molecules in order of increasing boiling point from lowest to highest. So correct, Reese, yeah. If it's a polar molecule, we're going to have dipole-dipole forces, right? Because a polar molecule will always have a permanent imbalance of electron density. So this is another type of that question that we'll see of how do we figure out boiling point. If we look at these molecules, again, they're all about the same size. So I can't say larger the molecule, higher the boiling point. It's going to come down to our intermolecular forces. So if I look at C, molecule C is just carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, non-polar, non-polar, non-polar. That's just going to have London dispersion forces. That's going to be the lowest boiling point we have. So I'm looking, C should be first, so I can cancel out A, I can cancel out D. Next, I take a look over here. I've got a carbon-chlorine bond, which is polar. So that means this molecule has London dispersion forces and dipole-dipole. So that would be next for my boiling point. So D. So now I can cancel out B, but we should still figure out the remaining of these. Right, if I look at B, molecule B, I've got a hydroxyl group now, so I'm polar and I have hydrogen bonding. So molecule B, London dispersion forces, dipole-dipole, and hydrogen bonding. And then when I get to molecule A, now I have two hydroxyl groups, even more hydrogen bonding, the higher the boiling point will be. So overall, choice C. And again, this is that case where all the molecules are about the same size. So I want to go to which one has the strongest intermolecular force. So London dispersion force, weakest force, lowest boiling point. Then we add in dipole-dipole, a little bit higher in strength, higher the boiling point. We add in hydrogen bonding, right? Strongest force, it's going to have the highest boiling point of those listed. Did that make sense, Karine? All right. So question 18, spontaneous or non-spontaneous, right? Yeah, Callie, ion dipole are the same strength as hydrogen bonding. They're 15 kilojoules per mole. None of those examples had ion dipole because for ion dipole, we need to see an ion in solution. So sodium +1 or chloride -1, right? We need to see an actual ion to have ion dipole forces. So something that's spontaneous, right? We know that happens. We've seen that happen, right? So metal rusting, that's spontaneous, right? Rusted metal exists in this world. That is spontaneous, right? Combustion of a rocket fuel, right? Combustion of a rocket fuel, again, that happens, right? That's spontaneous. And if you're not sure, just flip that, right? Do we see a rusted piece of metal turn into a brand new piece of metal? No, we don't see that because it's non-spontaneous, right? The reverse process is spontaneous. So have you ever observed solid sodium chloride leave water and precipitate out from solution? No, when we add salt to water, the salt dissolves, it ionizes in the water and goes into solution. It doesn't precipitate out of solution. So that would be non-spontaneous, right? Do we see water breaking up into hydrogen and oxygen? No, right? That would also be non-spontaneous. Because actually the opposite of this, right? Hydrogen reacts with oxygen in rocket fuel. So the opposite would be the hydrogen oxygen splitting up and making something else, or the water splitting up and making hydrogen and oxygen. So that makes that non-spontaneous. So basically, if it happens, yeah, exactly. If you can see it, you know it's happened, it's because it's spontaneous. If you've never observed it happening, right? Non-spontaneous. All right, we're going to take our next break there.